Pavlov's dogs beyond the bell and saliva introduction. Ivan Pavlov's early 20th century experiments that a neutral stimulus, the bell, could acquire the power to elicit salivation when paired repeatedly. Today, however, classical conditioning is often reduced in textbooks to the shorthand ring bell drool, obscuring a rich tapestry of temporal dynamics, associative complexity, and contextual modulation. In this essay, we move beyond the oversimplification to examine three critical extensions of Pavlovian learning. 1. The influence of timing through delay and trace conditioning. 2. The formation of higher-order associations. Temporal parameters in conditioning. Delay versus trace. At the heart of classical conditioning lies the temporal relationship between the conditioned stimulus seeds. Two primary paradigms illustrate how timing modulates learning. 1. Delay conditioning. In delay conditioning, the CS onset precedes the US. For example, Pavlov might sound the bell and maintain its ringing until the food is delivered. This overlap facilitates a robust association. The neural systems can directly link the ongoing CS representation to the impending US, yielding relatively fast acquisition of conditioned salivation. 2. Trace conditioning. By contrast, trace conditioning introduces a silent interval, the trace, between the CS offset and US onset. The bell rings, stops, and only after a brief pause does the food arrive. Successful learning thus requires the dog to maintain a memory trace of the bell during the gap. This form of conditioning is more cognitively demanding. It recruits hippocampal and prefrontal circuits involved in working memory. As a result, trace conditioning typically produces slower learning, weaker responses. Researchers have illuminated how classical conditioning intersects with broader principles of temporal coding, memory retention, and neural circuitry beyond the simple bell-drool schema. 2. Beyond first-order, higher-order conditioning. Pavlov's original demonstrations involved first-order conditioning, where the CS directly predicts the US. Yet learning does not stop there. Animals and humans readily form higher-order associations, extending the chain of predictive cues. Second-order conditioning. After a dog has learned that bell food, a light sees, can be paired with the bell sees. In the absence of food over repeated light bell pairings, even though the light was never directly paired with food. Sensory preconditioning. In another twist, two neutral stimuli, e.g., light and tone, can be paired before any condition. If the tone is later paired with food, the previously co-presented light also begins to elicit salivation, demonstrating that associative links formed prior to the US can retroactively gain significance. Higher-order conditioning reveals the layered, hierarchical nature of associative networks. Organisms build webs of predictors, enabling flexible and rapid inference. Context and internal state shaping conditioned responses. 1. Contextual modulation. The physical environment, or context, in which conditioning and testing occur, can profoundly influence expression of learned responses. A bell with food in context may salivate strongly when tested in that same context, but show attenuated responses in context. This context specificity arises because contextual cues themselves become part of the associative structure, acting as background stimuli that gate retrieval of the CS-US memory. 2. State-dependent learning. Internal physiological or emotional states can similarly serve as contexts. A rat condition, while hungry, may fail to show the same learned fear response. Conversely, if tested under the same state in which learning occurred, conditioned responses are more readily retrieved. These findings underscore that interoceptive cues. 3. Renewal and reinstatement. Even after an aversive conditioned response is extinguished by repeatedly presenting the CS without the US, changing context or re-exposure to the US alone can trigger a renewal or reinstatement of the response. Such phenomena highlight that extinction does not erase original learning. Instead, it overlays a new memory that is highly context-specific. By appreciating the interplay of context, we recognize that conditioned behaviors are fluid, subject to modulation by both where an organism finds itself and how it feels. Conclusion. Pavlov's pioneering work laid the foundation for understanding how neutral cues come to predict biologically significant events. Yet to reduce classical conditioning to a simple bell-drool equation does disservice to the nuanced architecture of associative learning. By examining temporal dynamics, delay versus trace conditioning, exploring hierarchical chains of predictors, higher order conditioning, and acknowledging the power of environmental and internal contexts, we gain a richer, more accurate portrait of Pavlovian processes. This expanded perspective not only deepens our theoretical grasp, but also informs practical applications from timing treatments, underscoring that, in the realm of conditioning, the story is always far more intricate than the bell alone.